Dear students, welcome to the lecture 2, which deals with the number systems. And so after completion of this particular uh, lecture, we'll be able to list the number systems, represents the decimal number in the binary, convert binary numbers to decimal, and then conversion among other number systems. Now, we know that number systems, basic number systems, are four types: decimal, binary, octal, and hexadecimal. Decimal means the range is from 0 to 9 and the base is 10. Binary means there exists only two digits, 0 and 1. The base is 2. So this base indicates the number of distinct digits in a particular number system. So in a decimal, there are 10. So base is 10. In binary, there are only two digits. So the base is 2. In octal, there are 8 digits, 0 to 7. So the base is 8. In hexadecimal, the range of numbers is 0 to 9 and then A to F. So A is nothing but 10 in decimal, B is nothing but 11 in decimal, and C is nothing but 12 in decimal, and D is nothing but 13 in decimal, and F means 15 in decimal. And the base is 16. So this is how the hexadecimal number system represents. So 0 to 9 and 8 to 10. So we don't, right? So these are the four basic number systems: decimal, binary, octal, and hexadecimal. Of course, the base also gets varied according to the version, right? But these are the four decimal numbers. These are the four number systems. And then a review on the decimal systems would be like this. We know this. What would be the weight of, suppose if I take 123 as one decimal number, 123 as one decimal number, the weight of this is 10 power 0. The weight of this is 10 power 1, and the weight of this is 10 power 2. That is hundreds place, 10 place, and units place. You know this. And this 123.456. So the weight of 4, that means after decimal point, would be 10 power minus 1. And 10 power minus 2, like that it will go. So you know this concept. And what is binary number system? So most of the digital systems use a binary logic, where there will be having only two values, that is logic 0 and logic 1. In some systems, 0 indicates 0 volts and plus 5 volts is indicated with logic 1 value. So this is applicable when you are designing a circuit, right? So as of now, this is not required, but you remember in some circuits, there are having only two voltages, 0 volts and 5 volts. So it indicates a logic 1 and the 0 volts indicates a logic 0. And binary to decimal, it's very simple. Suppose if you take 1010 as a binary number, what is its decimal equivalent? Very simple, right? So the way, as the base is 2, the weights of this would be in the powers of 2. So this would be 2 power 0, 2 power 1, 2 power 2, and this is 2. So 1 into 2 cube, 0 into anything will be 0, 1 into 2 power 1, and 0 into 2 power 0. So answer would be, this would be 8, 2 power 3 is 8, and this is 2. So the answer will be 10. So 10 equivalent is nothing but 1010 in binary. So this is how we convert a binary number to decimal. So very simple, use the same concept. You can find the answers like this. And suppose there is a fractional number like this. For example, if you consider this one, 1011.11. What is the weight of this? 2 power minus 1. And what is the weight of this? 2 power minus 2. This is 2 power 0. And this is 2 power 1. And this is 2 square. And this is 2 cube. So 2 cube plus 2 power 1. 8 plus 2 plus 1, 11. And this is 1 into 2 power minus 1 is nothing but 0.5. 1 into 2 power minus 2 is nothing but 0.25. So 0.5 plus 0.25 is nothing but 0.75, and this remains the same. So final, the answer is 11.75. So this is how we convert a fractional binary number to fractional decimal. And reverse, if a decimal number has to be converted into binary, what is the procedure? Suppose if the 19 is there, how do we convert this? Divide with 2. 2 nines are 18, remainder is 1. 2 fours are 8, remainder is 1. 2 twos are 4, remainder is 0. And 2 ones are 2, remainder is 0. You repeat until the quotient becomes 0. So finally, write the answer from the bottom. So final answer is 0, 1, 0, 0, 1. You can discard this 0 because left side, if you are having 0, that doesn't changes the final value. So the final answer is 1001. This is another format of getting the binary equivalent. So you can use any one of these two techniques. Next is octal number system. As I said, octal number system, the range is only from 0 to 7. After 7, you'll be getting 1 0, which is equivalent to 8 in decimal, right? Because in octal, there doesn't exist 8, 9, right? 8 and 9 doesn't exist in octal. So that's right. After 7, you will be getting 1 0, which is nothing but 8 in decimal. 1 1, which is nothing but 9 in decimal. Right? So I'm saying 1 0 in octal is equal to something in decimal. How do you do that? This is 840. This is 8. Same as you do binary to decimal. The similar fashion you have to do octal to decimal. This is 1 into 8 plus 0. It's nothing but 8. Answer is 8. Now, octal to decimal, just now I said 172. Octal means the base is 8. So weights will be in the powers of 8. Very simple, right? So once if you understand binary to decimal and decimal to binary, it would be same concept for other number systems, except the weights get changed. That's it. So octal to binary, these are the binary representation. Now, every octal digit is equivalent to 3 bits, 3 binary bits. Why it is 3 binary bits? So here, uh, I'm saying every octal digit is equivalent to 3 binary digits. Why it is so? Because, because in an octal number system, the maximum number is 7, which can be represented with 3 ones. So 3 bits, nothing but 3 bits. So if 7 is represented with 3 bits, automatically the lower values can be easily represented with 3 bits. So minimum number of bits required to represent an octal digit in a binary is 3. That's right. We can say every octal digit is equivalent to 3 bits of binary. Now, how to convert octal to binary? Very simple, right? Suppose the number 372 is there. 372. This is an octal. How to convert into binary? Represent every octal digit in the 3-bit format. 7 is nothing but 3 ones in binary. 0, 1. So this is an answer. Every octal digit is equivalent to 3 bits of binary. This becomes a binary. Base is 2. This base is 8. In a reverse fashion, if the binary number is given, split the bit pattern into 3 bits starting from LSB. So this is LSB actually. This is LSB. Split the bits into 3 starting from this. So if the question is given like this, right? What is the question? 1 0 0 1 0 1 0. So 1 2 3. Split it. 1 2 3. Split. 1 2 3. That's it. Right. So what is its decimal equivalent? 2. 7, 4. The answer is 470. Right. So this is how it works, right? You have to split into 3 bits. Additional examples are given. We will go through this, right? So in the next session, we will be discussing hexadecimal number systems. With this, so the concept remains the same, right? Even if you do for hexadecimal also the same concept. If you want to convert decimal to hexadecimal, divide it with 16. In a reverse, hexadecimal to decimal, multiply the weights of 16 with the corresponding digit of a decimal. So thank you, students. We will be discussing hexadecimal number in the next lecture. Thank you.